All right, this is AP, AB, and BC Calculus. We're doing Unit 6, Section 9, which is integrating using substitution. So essentially, this is what we would call U-sub, right? So what we're doing now, this section is U-sub, and U-sub is super important. So most other forms of integration that you're going to learn, and you will learn other forms, use some simple U-sub somewhere in the problem. So this is super duper incredibly important. This is a really big section. So U-sub is a bit like the reverse chain rule. When to use it? If there's a function in your function in an integrand, okay? We're going to walk through lots of hints about how to choose U, but essentially the hints on choosing U, it is usually inside another function, and some multiple of the derivative of U, aka du, will appear somewhere else in the integrand. What's the goal of U-sub? Well, the goal is to take a really complicated, disgusting-looking integrand and make it look like some simple antiderivative rule that we learned in 6.8, right? So the last video. So here are some examples of integrals that would use U-sub. See how the 3x is inside a sign? Well, that would be my u, okay? See how this x to the 5th is inside the cosine? That's my u, and see how some multiple of du appears outside of that in the integral? See how there's an x to the 4th and a 5x to the 4th, right? Here, du is just dx for the first one, and there is a dx here, right? See how an x to the 4th and a dx appear in this. So here, my u would be the inside of the root. See, that's my u, right? And sure enough, du is an 8x dx, which appears directly in the integral. Here, my u would be the function that's inside something. Being in the denominator counts as being inside something because that's inside a -1 exponent. So that's my u, and my du would be a 2x plus 3 dx, which is exactly in that integral. So essentially, using U-sub allows me to take an integral that's really ugly and simplify it so it looks just like one of those antiderivative rules we memorized. Sometimes there are multiple possible candidates for U in a really complicated integrand, but only one of them actually works out the way you want it to. That's okay. Sometimes you're going to pick a U, you're going to start walking through it, and then you're going to realize that what you've chosen is making the problem worse, not better, and you're going to stop and pick the other option, right? Sometimes we take the wrong step first, and that's okay. It's the ability to recognize that something's gone wrong and change course that's really important. All right, so moving on. Let's walk through a simple example of U-sub. So we're doing indefinite integrals for now. We'll talk about definite integrals later in the video. So we're going to choose a u that is usually the inside function. Here, my u is going to be 3x. So here's u equals 3x. I'm going to pick my u and I'm going to find du. So by that I mean differentiate u. So the derivative of u is 3 times the derivative of x. I'm then going to solve that for dx. So du over 3 is going to be able to replace my dx. So I have a way to replace 3x with u, and I can replace dx with du over 3. So that was this step right here, right? I chose my u, and then I differentiated. So now let's do another step, right? So replace all the values of x with u stuff, okay? You don't know how to integrate multivariate things yet, meaning you don't know how to integrate with different variables in your integral, so you have to replace everything. So sine of u, because that's what I called 3x, and then instead of dx, I'm going to put a du over 3. Well, that means that I could just yank a 1/3 out in front of the sine of u du. So now I have a simple antiderivative rule, which is the integral of sine. Yay, simple antiderivative rule. So when I integrate sine, I get negative cosine of u, right, plus c. The last step I need to do, right, which is right here, is I need to replace all the u values with x stuff. So I'm going to get negative 1/3 cosine of 3x plus c. And that's my answer. So that's how U-sub works. So we take something, now admittedly, sine of 3x probably doesn't look horribly, violently complicated to you, but some of the other integrals that we're going to deal with will look really complicated. So we're taking something that has some complex parts, something that's a little confusing because it's got a function and a function. We're making it look like a simple antiderivative rule that we have, of course, memorized with note cards, and then we're going to go ahead and anti-differentiate. All right, so let's do an example. All right, so here, right, I'm going to call the inside function u. My u is going to be the 4x squared plus 3, the thing on the inside of another function. In this case, it's on the inside of a square root. I'm then going to find du, right? So my du is going to be the derivative of 4x squared is going to be an 8x dx because the 3 is gone, right? That differentiates to 0. And I'm going to solve for dx. So du over 8x is going to be my dx. So now when I replace this stuff, I have an 8x here and a root u because I called the stuff on the inside u. And then my dx is a du over 8x. Well, it's not an accident that those cancel. So I'm going to get that this is just the integral of root u du, which is a simple antiderivative. Remember that that's u to the 1/2. So we're going to up the power by 1, so u to the 3/2, and divide by the new power, but hopefully we're getting to the point where we recognize that we can just multiply by 2/3 instead. And then my last step is to replace my u with a 4x squared plus 3 all to the 3/2. So that's my answer. And notice that I don't forget the plus c. All right, let's give it a try. So now you're going to try this one. Now notice you actually could FOIL this out, right? Oh, and as a side note, because see how the exact du appeared in the integrand? That means that some of you might be able to cheat and not do this step. You might be able to just look and say, oh, I could replace this 8x dx with a du. And that works fine if the exact du appears in the integrand. But as we progress to harder problems, that won't be the case, and so you just have to be a little more heads up about it. All right, so go ahead and give this a try. Don't FOIL this out. I know that you probably are thinking, hey, maybe I could, but that's a terrible idea. So your u is going to be the function that's inside another function, and in this case, that's an x cubed minus 4. My du is a 3x squared dx, which again is right here, right? That's exactly what the integral looks like. So if you're able to jump right to saying, oh, I get it, this is a u to the 4th times a du, that's great. If you're not, right, you would solve for dx, and you'd plug in and say, oh, okay, this is a 3x squared times u to the 4th times a du over 3x squared. You'd cancel the 3x squareds, and it would land you here. Either way, doesn't matter to me. When you anti-differentiate, you get u to the 5th over 5 plus c, but then it's not really a u, it's an x to the 3rd minus 5. Oh, I don't know where I made that a 4 from. Sorry, my bad, it's a 5. X to the 3rd minus 5 raised to the 5th all over 5 plus c. If you like it that way, that's fine. If you'd rather write it as a 1/5 in front of all of that, that's totally fine. Sorry that I accidentally made it a 4 there. It's totally a 5. All right, either of those would be totally fine. All right, and again, U-sub is one of those skills that it's going to show up in a lot of integration problems. If not, it's almost every integration problem will have some kind of U-sub, whether it's complicated or simple, whether it's a minor step or a major step. It's sort of like factoring, right? Factoring is its own standalone skill, and it's really important, but factoring shows up in almost every problem. And that's going to be true with U-sub as well. So just you want to get really familiar with this. All right, so let's try an example 2. So now du is not going to appear exactly in the integral. A multiple of du will. So let's go ahead and, my u is probably the function that's inside another function. So my u is x to the 5th. My du is going to be a 5x to the 4th dx. When I solve this for dx, I get du over 5x to the 4th is my dx. So now, when I replace this, I have an x to the 4th, a cosine of u, and a du over a 5x to the 4th. Well, look what happens to the x to the 4th. They cancel, and I'm left with a 1/5 in front of the integral of cosine of u du. Well, this is one of the things I memorized. So when I integrate cosine, right, I should get sine. So I get 1/5 the sine of u plus c, but then my final answer needs to replace the u with an x to the 5th. Notice that as soon as I integrate, I write my plus c. All right, let's go ahead and give this one a try. So my u is inside another function, right? So my u is going to be the x to the 4th that is inside the exponential function, which means my du is going to be a 4x to the 3rd dx. When I solve for dx, I get du over 4x to the 3rd is my dx, and then what you'll notice is that pretty quickly that x to the 3rd is going to cancel, right? Because this is a du over a 4x to the 3rd. They cancel. So I get a 1/4 times the integral of e to the u du. Well, that's one of those antiderivative rules we know. In fact, it's the easiest one because when you integrate e to the u, you just get e to the u. So I'm going to get that this is 1/4 e to the x to the 4th plus c. All right, moving on. All right, so now there's some random extra stuff, right? I did kind of quantify that these are getting more difficult as we go. So hopefully it's pretty clear that my u should be the x plus 5 because it's inside a function. And so I get my du is dx, and everything's seeming fine. I get an x times a u to the third times a du. Uh-oh. We don't know how to deal with mixed integrals. I need u stuff here, okay? So I need to be able to replace this with u stuff, but it didn't naturally happen. So in order to do that, I'm going to have to take my u formula and say, oh, u minus 5 is the same as x. So I'm going to use that to replace the integral. So I'm going to get that this is a u minus 5 times a u cubed du. Now you might say, Hogan, how is that better? Well, here's why it's better. I can't distribute this x into a binomial that has a power on it because that's not how it works because of the power. But I can distribute a monomial to this binomial that doesn't have a power. So this is now a u to the fourth minus 5u cubed du. Well, now it's a simple power rule. So I raise the power by 1, divide by the new power. Raise the power by 1, divide by the new power, plus c. So I'm going to get that this is x plus 5 to the fifth, all over 5, that's a lot of 5s, minus a 5/4 x plus 5 to the fourth plus c. And again, if you wanted to write that first one as a 1/5 in front of the x plus 5 to the fifth, you certainly could. So the issue here is this random extra stuff. The problem is this tedious, frustrating x. That's the issue. All right, so give this one a try. It's the same idea. All right, so same idea. My u is almost never x. In fact, the only exception to u being x is if you're dealing with arctrig, and we'll get to some of those at some point. So my u is probably inside the other function. So my u is x minus 3. Sorry, brain died a little. X minus 3, which means my du is just dx. So that's great. Everything's going fine until I plug in and realize that, uh-oh, there's this pesky, frustrating x. Right? I can't integrate with that x there. So I have to take this formula that I have and say, oh, u plus 3 can replace an x. So again, what makes that better is that I can't distribute into a root. That's not math you're allowed to do. But what I can do is distribute this u to the 1/2 times this binomial that has no power on it. So I'm going to get that this is a u to the 3/2, right, because it was a u to the first and a u to the 1/2, plus a 3u to the 1/2 du. Now I can integrate. So I'm going to get that this is a raise the power by 1, so that's a u to the 5/2, and then divide by 5/2, but we're just going to get to the point where we accept that that's multiplying by 2/5, right? This is a 3. When I raise the power by 1, I get 3/2, right? So I have a 3. This is a u to the 3/2, and then times 2/3, which is nice because the 3's are going to cancel, plus c. So I get that this is a 2/5 my u, which was x minus 3, to the 5/2, plus a 2u, which was x minus 3, to the 3/2, plus c. So again, what's tricky about these is that there's that one part of the integrand that just doesn't turn to a u naturally. All right, let's go ahead and talk about when we have multiple options for u. All right, so I want to integrate and there's multiple options for u. So here's the issue. You're probably thinking, could it be a 3x? That seems to be inside some other things. But here's the problem. If your u is 3x, it's still going to look really complicated. This is still going to have a cosine and a sine squared, and it's going to be really frustrating, even if I replace this 3x, right? So that's not enough. But then your next question might be, okay, well, what other function is inside a function? If we rewrite this as what we'd have to type in our calculator, which is sine of x quantity squared times cosine of, or sine of 3x quantity squared times cosine of 3x dx, then it becomes a little more obvious. The function that's inside that would make my life easier is if I pick u to be the sine. So u is sine of 3x, which means that my du is going to involve a chain rule, right? The derivative of sine is cosine, but then I have to differentiate the 3x. So what's going to happen is I'm going to get that my du is a 3 cosine of 3x on the bottom, right? So du over 3 cosine 3x, that's going to be my dx. Now that actually works out really well because look, there's that cosine that I want to get rid of, right? That cosine 3x. So now when I plug my stuff in, I'm going to get that this is a u squared because I made this whole inside thing be u times this cosine of 3x. And then my dx is a du over 3 cosine of 3x. Well, look, that's great. And I get that this is a 1/3 in front of a u squared du. So I up the power by 1, which would be a u to the third, right? Divide by the new power plus c. And I get that this is a 1/9 sine of 3x, because that was my u, to the third plus c. And it's okay to write it this way. The way you probably more commonly see it is with the cubed between the sine and the 3x, right? That's where we usually put it. That's better, right? So this is better. But notice that in order to see which function was on the inside, I really needed to think about the way that this would look if I were typing it in a calculator. And again, the reason I didn't pick the 3x is it was just way too simple, right? And the cosine wasn't inside another function, right? So if I pick the 3x, what's going to happen is I'd end up with a sine squared still and a cosine still, and it would still be really ugly. All right, so let's go ahead and try another one. So try this one. This one's a little bit trickier, actually. So I didn't mean to necessarily give you something super tricky. But there are two possible, okay, so there actually are two u's that would work out fine here for the record. But it's a little bit tricky, right? So when you look at this, right, the first thing I want your brain to realize is that when you differentiate tangent of, let's say, x, right, you get secant squared of x, right? So here's what I want you to notice. If you chose this to be your u, then this would be a multiple of du, right? The other way to think about this one, so let's say I chose that. Let's say I chose to start with that. Let's say I said, wait a second, u is tangent of 4x. That means that my du is a secant squared of 4x, which is convenient because it shows up right there, times the 4 dx, right? Because the chain rule, I need the 4. So I get the du over a secant squared of 4x with a 4 in front, right, is my dx. If I did it that way, I'd get that this integral, so let's just draw an arrow down here, that this integral was equal to secant squared of 4x times my u, right, times du over a 4 secant squared of 4x, right? The secant squareds would cancel, and I'd end up getting that this is a 1/4 the integral of u du. Now that's just a u to the first, so that's a 1/4 u squared over 2 plus c. I'm going to get that this answer would come out to a 1/8 tangent squared of 4x plus c, and that's great. Interestingly enough, there might be a few of you watching this video that thought of a different option, and I just want to throw that out there. So there is an interesting, clever other option. So option 2, and this doesn't always happen, but there is a second option that would work here. If you were to treat this secant squared as a secant times a secant, because that's what secant squared is, right? What you'll notice is that if you picked this as your u, this would be a multiple of your du, right? Because the derivative of secant of something is secant tangent. So if you chose to do this, if you made your u secant of 4x, then your du would be secant tangent of that 4x, right? Secant 4x, tangent 4x, times the 4 dx. So you'd get that your du over a 4 secant 4x tangent 4x is equal to dx. Well, if you did that, then it would mean that this entire integral could be replaced as a u times a 1/4 du, right? Because essentially the secant 4x tangent 4x would cancel. This secant tangent 4x and this secant. So you'd get that this would be a 1/4 the integral of u du. So you'd get this is 1/4 u squared over 2 plus c. And so you'd get that this is a 1/8 secant squared of 4x plus c, and that's also right. So here's the trick. They don't look like the same answer, right? So using option 1, we got that the answer was 1/8 tangent squared of 4x plus a constant. And using option 2, we got that the answer was 1/8 secant squared of 4x plus c. How are they the same? Because you might be really frustrated and say, hey, wait, Hogan, they're clearly not the same. I don't understand. Well, the way that they're the same lies in a trick about the arbitrary constant. Remember that there's a trig identity that tells you that tangent squared plus 1 equals secant squared, right? So let's say I just take my option 1 answer and replace my tangent squared 4x, right? Because that doesn't have to be theta, right? That could be 4x, right? So tangent squared of 4x plus 1 would be the same as secant squared of 4x, right? With me, hopefully, so far. So let's just take a second and let's replace this tangent squared with a secant squared of 4x minus 1, right? Like I can move the 1 to the other side. So I'm going to make this minus 1 on this side, right? So so if I replace the tangent squared, or I could have replaced the secant squared over here. I guess it doesn't really matter, but I'm going to pick this one since I already did it. So let's say I replace that tangent squared of 4x with a secant squared of 4x minus a 1. Because I can, because it's a trig identity that says I can. Well, wouldn't I get 1/8 times secant squared of 4x? Sorry, get rid of that parenthesis. Minus 1. And for the record, you don't, so again, we're trying to show that these two are equal, right? Plus c, my bad, I forgot my plus c. So plus some arbitrary constant. Well, wouldn't that be a 1/8 secant squared of 4x minus a 1/8 plus an arbitrary constant? Well, isn't this just a different arbitrary constant? So couldn't I say that this is 1/8 secant squared of 4x plus, let's just say, some other arbitrary constant? Well, isn't that the same as this? So the reason that they're both the right answer in this case is because of the nature of that arbitrary constant. So is that frustrating? Absolutely. Do I expect that you'd see it as a multiple choice problem? No. The way that one like this is typically worded is they might give you one that is multiple choice and ask you which of the answers is a possible answer, or how many of these answers, like Roman numeral 1, 2, and 3 are possible answers. Notice you didn't have to integrate it both ways to get there. You just had to also know a trig identity. There are a couple different ways to look at that. Again, that was definitely a difficult problem. All right, let's go ahead and walk through E5. So this one's tricky because I see two possible candidates for essentially the way to treat the U. The U might be, I might want to use the U on the bottom, but then I'm not going to be able to, now it turns out that the bottom is the same as the inside the exponential right here, but the trick is that I really need to somehow find a way to make this thing inside the e to the x be my U. It turns out it's the same as the bottom in this one particular instance, but the reason I say that is that multiplying and dividing can cancel the root on the bottom here, but it can't cancel the thing inside the e to the x. So I'm going to make the thing inside the e to the x be my u, right? Remember that's an x to the 1/2. And that means my du is going to be a 1/2 x to the negative 1/2 dx. Or if we clean this up a little bit, that's a 1 over 2 root x dx. When I solve for dx, I'm going to get 2 root x times du is equal to my dx. So I'm going to plug this in, and what's going to happen is that root x on the bottom is going to go away. So I have an e to the u over root x times a 2 root x du. Well, the root x's are gone, and I get that this is a 2 times the integral of e to the u du, which is just a 2 e to the u plus c, which means I'm going to get 2 e to the root x plus c. All right, moving on. All right, so here, the question is the u the thing on top or is the u the thing in the bottom, right? Well, being on top of a fraction isn't actually being inside a function, right? Because that just means you're to the first power. But being in the denominator means that you're actually to the negative 1 power. So I'm going to try making my u the denominator. And my du will be a 2x plus 3 dx. Well, look, that's convenient. That's literally the top. So if you can just spot that this is the integral of du over u, or if you like it better, you can write it as a 1 over u du. They're the same thing. Either way, it's going to integrate to the natural log of the absolute value of u plus c. So my answer is the natural log of the absolute value of x squared plus 3x plus 1, all plus c. All right. So u sub with bounds. So the bounds of an integral are the values of the variable of integration, which you can spot by looking at the d blank, right? So when you see an integral, you have an integral symbol, blank, and d something. This is the integral, the variable with which you're integrating to. If you're integrating from a to b, then these bounds represent x values if this is an x. And if this were a t, then these would be t values, right? And this were whatever letter it is, those represent those values. So if you change the integrand to have a du, then you also have to change the bounds to match. There is another way to do this, in which you essentially write the indefinite integral off to the side and do all of the work, as long as you clearly don't say that the definite integral and the indefinite integral are equal, because they're not. And then you can loop back and deal with the plugging in after you've done all the work off to the side. That's the way I tend to do these problems, and we're going to walk through all of your options. Honestly, the only reason that I changed the bounds on U-sub instead of doing all my work off to the side is if it's a question where I'm specifically asked to do so. So we're going to walk through both options, though, so you can see it. Okay, so we're going to talk about changing the bounds, which is the official way, versus doing separate work, which is my way. Okay, so here's how you would be asked to do it if you were going to change the bounds. You would pick your u, which in this case is definitely the only inside function option I have, so 5x minus 2, which means my du is a 5 dx, so I'll replace du over 5 in the dx spot. So when I go to do that, I also have to change the bounds, right? So I did this piece. If I'm going to change the bounds, I have to deal with them too. So the bounds were x equals 1, right? But since u is 5x minus 2, I'm going to have to replace this with a u is 3. The other bound was x is 0, but since u is a 5x minus 2, I'm going to have to replace it with a negative 2. So if you're going to replace your bounds, you're going to replace this integral. The second I plug the u stuff in, I have to change the bounds at the same time. So I'm going to get a negative 2 to 3 of u cubed times du over 5. So see how when I changed the integrand to have u's, I had to change the bounds to also be u's. The advantage to doing this is when I'm done, I'm not going to have to change my stuff back to x's, because I'm not being asked to find the indefinite integral value. I'm just being asked to find a numerical value. So when I integrate, I'm going to get this a 1/5. This will be a u to the 4th over 4, evaluated from negative 2 to 3, right? So when I plug in, I'm going to get a 1/5 times, this is going to be an 81/4 minus a 16/4, right? I don't feel like mathing. 65, probably? Yep, sounds right. So I'm going to get a 1/5. This is going to be a 65/4, which means if I cancel the 65 and the 5, I should get 13/4 as my answer. And that's fine, right? That's one way. Notice I never bothered to change the x back. Here's how I do it, and you can totally not do it this way, but this is what I do. I make a separate spot where I say work, and then I do the indefinite integral. So what I do is I do all the same stuff that we just did. Right? All the same stuff, but notice I do it without bounds. I just very clearly separate my work and say, hey, this is just the work. It's not me saying this thing is not equal to this thing. It never will be. It's not me saying that. So I get that this is the integral of a 1/5 u to the 3rd du, right? When I up the power by 1 and divide by the new power, I end up getting that this is essentially a 1/20th u to the 4th, right? And I don't bother with the plus c because I'm cheating and I know there are bounds. So I get that this is a 1/20th 5x minus 2 to the 4th, and that's what I plug in at the top. So I do all that work, and then I say, cool, this is this from 0 to 1. So then I plug in and get that this is a 1/20th, right? When I plug in 1, I end up getting a 3 to the 4th, right? Because that's what we'd get if we plug in a 1. Minus when I plug in 0, I get a negative 2 to the 4th, which is a 16, right? So I get that this is a 1/20, and then this is an 81 minus 16. So I get 65/20, which simplifies to a 13/4. Same answer. It doesn't matter to me which way you do it. I really don't care. But if you do it my way, what I am going to say is you need to very clearly separate this work and not say at any point that that's equal to the indefinite integral. Like draw a box around it like I did and make it clear that this stuff is all equal and this stuff is equal to itself, but at no point are the two the same. So again, I really don't care which one you do. Moving forward, it doesn't matter to me, but I wanted to show you the two different options. Okay, so again, I'm going to suggest that it's not really worth changing the bounds. I really like my way, so I'm going to do my work separately. It's up to you. At the end of this video, I'm going to show you exactly how you would have to change the bounds in certain multiple choice questions so that you know what's up, all right? So I know that cosecant squared is an antiderivative. So I think that if I just make u my 3x and my du a 3dx, which means that I'll replace my dx with a du over 3, right? I think that I get that this is a 1/3 the integral of cosecant squared u du. Cosecant integrates to a negative cotangent. So I get, here, wait, let me buy myself a little bit more space. I get that this is a negative 1/3 cotangent u, right? Which would be a negative 1/3 cotangent of 3x. So now, having done my work completely and totally separately, I come up here and say, oh, cool, this is a negative 1/3 cotangent of, that's a cotangent, come on, Hogan, cotangent of 3x evaluated from pi over 18 to pi over 12. Notice at no point did I say that this indefinite integral was equal to the definite integral. I didn't. I very separately said, hey, this is my work. And then when I plug in, I'm going to get that this is negative 1/3 cotangent of, when I plug in pi over 12, I get 3 pi over 12, which is a pi over 4, minus a negative 1/3 cotangent of, when I plug in pi over 18, I get a pi over 6. Right? So now you're going to have to do a couple things that involve the unit circle, so good times. So I'm going to need the cotangent of pi over 4, and I'm going to need the cotangent of pi over 6. So you kind of got to know where those are. So here's pi over 4, right? Tangent and cotangent are both 1 at that point, right? So that's a 1. So this is negative 1/3 times a 1, right? Pi over 6, though, is the point root 3 over 2 comma 1/2. Cotangent is cosine over the sine. So it's a root 3 over 2 divided by a 1/2. When you flip and multiply, you're just going to get that this is a root 3. So this is plus a 1/3 times a root 3. And that's really as good as my answer gets. I mean, you could try and clean it up if you want. But realistically, your answer is essentially a negative 1/3 plus a root 3 over 3. Or if you want, I guess you could write it as a root 3 minus 1 all over 3. And it doesn't get much better. Like, those are your options. There's no nice way to write it. All right. So you're going to go ahead and try this one. Again, I don't care how you do it. You can change the bounds if you want. I'm not going to, because I've been doing this for decades and I just don't care to change the bounds. So sine of 2x dx, again, I'm not at any point saying that this thing is equal to my definite integral, right? I'm going to guess that my u is just 2x because that's the inside of the function and it's a pretty friendly function. So du over 2 is my dx. So I'm going to get this is the integral of 1/2 sine of u du. Well, I know that sine integrates to negative cosine, so I'm going to get a negative 1/2 cosine of u, right? And so I could just jump up here now and say, cool, I get it. That's a negative 1/2 cosine of u, which was 2x, right, from 0 to pi over 8. So this is going to be a negative 1/2 cosine of pi over 4, because that's what 2 pi over 8 would be, minus a negative 1/2, so that'll be plus a 1/2 cosine of 0, right? So this is a negative 1/2 of a root 2 over 2 plus a 1/2. And again, you're going to find yourself in a situation where this doesn't get much better. You can leave this as a negative root 2 over 4 plus a half if you want. You could get a common denominator if you want. You could make them all over 4. It doesn't really matter. It doesn't get much better. That's about it. That's fine. All right. Okay, so same thing. Again, you can change the bounds if you want, but I'm just not going to live that life. So I'm going to do my work separately, right? So I'm going to recognize that my u is probably the function that's inside the root, and that makes my du a negative dx. Now that's fine, except I'm going to have that annoying pesky x sitting here we've seen before. So I'm going to get an x root u times this negative du. Well, that's fine, but what am I going to do about this pesky x? Well, what I'm going to do is I'm going to use this to recognize that if I switch and add the x over and subtract the u, I get that x is 6 minus u. So this is the integral of a 6 minus u times a u to the 1/2, with a negative out in front that we'll deal with in a sec. So I get that this is a negative 6u to the 1/2 plus a u to the 3/2 du, right? When I integrate, I seem to get that this is a negative 6. This will be a u to the 3/2 times a 2/3, which we'll deal with in a sec, right? Plus, this will be a u to the 5/2. That's not an x, my bad. So a u to the 5/2, so I would times by 2/5, right? So this is what I'm looking at, right? I'd probably cancel these guys and end up getting that this is a negative 4 u to the 3/2 plus 2/5 u to the 5/2. And then after all that, I need to remember what u is, so that's good times. So when I get up here, right, when I get up here to clean this up, and you can see that these are no fun, I get it, it's fine. So when I get up here, I'm going to recognize that this is a negative 4u to the 3/2 plus a 2/5 u to the 5/2, evaluated from -3 to 2. And this is not going to be particularly fun, so we might end up needing space. But to make it really clear that this work is separate, I'm actually going to go out of my way. Now, it's a little more obvious here because I use different colors, but you won't always have that luxury. I'm going to make it really clear that that's separate by like boxing it off and saying, hey, I know that these things aren't equal, right? So when we get down here, we're going to go ahead and take a quick screenshot of that because I don't feel like having to recopy it, and I'm kind of lazy. So we take a screenshot of this ridiculously, oh, come on. Take a screenshot of this ridiculously disgusting thing. And then scroll down a little. All right, there we go. Super fun, totally disgusting. Good times. All right, awesome sauce. So, not all U-sub is this tedious. It just, this happens to be a little tedious. All right, so when I plug in, right, I'm going to get that this is a -4. When I plug in the 2, right, it's going to be 6 minus 2, so that'll be 4 to the 3/2, which we can clean up, right, plus 2/5, and again, this will be a 4 to the 5/2, which we can clean up, right, so that's the top bound, right, minus, when I plug in the bottom bound, I'm going to get a -4, 9 to the 3/2, right, which I can also clean up, so we'll deal with that in a sec, plus 2/5, 9 to the 5/2, right? So just a reminder, 4 to the 3/2 is easiest done as a root 4 to the 3rd, which is a 2 to the 3rd or an 8, right? So that's not an awful number. And 9, sorry, and the same thing's going to be true of the 5/2, my bad. So, so 4 to the 5/2 is best done as a root 4 to the 5th, which is a 32, because it's 2 to the 5th, right? And you can do the same thing with 9, right? So 9 to the 3/2 is a root 9 to the 3rd, right, which is a 27, and 9 to the 5/2 would end up being a 3 to the 5th, which is a 243. I get that that's no fun, but we'll survive. All right, so I end up getting that this is a -4 times an 8 plus 2/5 times, that's not fun at all, 32, right? Minus, in parentheses, this is going to be a -4 times a 27 plus a 2/5 times a 243, which nobody really wants to deal with. Okay, cool. So I get a -32, right, plus 64/5 minus, I don't really feel like doing that, but cool. So that'll be minus a negative, so that'll be plus, it's an 80 and 28, so it's a 108, right? And then this will end up being a minus 200, so that's 486, right? 486 over 5. And again, this is much meaner than you would likely see in most situations. So you're then going to combine these, I suppose. Again, I didn't necessarily mean to give you anything that was entirely cruel like this, right? If it was a 38, that'd be a 70. So it should be 6 more than that, right? So we should have a 76. So it should be 76. Yep, that checks out. So these come out to a 76. That's a 2 and a 20, so it's 422. So minus 422 over 5. That seems to check out. Yep. All right, I'm going to leave it like this. If you wanted to get a common denominator, I guess I'll feel guilty if I don't. All right, this is a 350 and a 30. This is a 380. So 380 minus 422 all over 5. That's a 42. Seems to check out. So I think we get a -42/5. I'm really not super stressed about it. It is what it is. I'm sure somewhere in that mess my math went wrong. Keep in mind you're not likely to see anything this ugly. I suppose we could cheat and use a calculator to double check. Let's see what happens. It's probably going to go awry. I'm just going to throw that out there. I'm not going to stress too much about it. If the math went wrong, you can double check me and let me know where it happened. So I'm going to go ahead and do math 9, which is function integrate. We're going to go ahead and integrate our y1 with respect to x from -3 to 2. and hopefully not go tragically awry. And what did I get? I don't remember what I got. All right, I got, yeah, that's right. Color me shocked. Yep. All right, cool. So that seems unlikely. All right, so let's go ahead and try another one, right? So same idea. I'm going to suggest that you separately do your work and then change your bounds. It's your business if you don't want to do that, but I'm going to suggest it's easier. So I'm going to do my work without the definite integral, right? I'm going to do my work on an indefinite integral because I think that's the easier option. So I'm going to say my u is x minus 5. My du is just a dx, right? So I'm going to get that this is the integral of an x times a u to the third times a du. This x is going to be the problem, right? So I'm going to recognize that u plus 5 could take the place of my x. So I'm going to get u plus 5 in parentheses times this u cubed, which means this is a u to the fourth plus 5u cubed with respect to u. When I integrate, that's a u to the fifth over 5 plus a 5/4 u to the fourth, right? That's what I'm going to use. And I just need to remember what my u value is. So this is going to end up being a u to the fifth over 5 plus a 5/4 u to the fourth evaluated from 3 to 5. Which is no fun, but hey, it's a little more fun than the last one. The good news at least is that when I plug in 5, I'm going to get a lot of zeros. So when I plug in 5, I'm going to get 0 over 5 plus 5/4 of 0. Hey, that's nice, right? Minus, when I plug in 3, I'm going to get that this is a negative 2 to the fifth over 5 plus 5/4, and this will be a negative 2 to the fourth. Hey, this is not awful. This is much nicer than the one I gave myself. So I'm going to get that this is a negative 32 fifths, right? And then the nice thing about this, right, is that this is going to be a 16. So I have a 5 times a 16 all over 4. I can cancel the 4 and the 16 and get a 4. So I'm going to get that this is a negative times a negative 32 fifths plus a 20, which I'm going to change into 100 fifths, right? So that's a negative 32 fifths plus 100 fifths, because that's what 20 would be the same as, right? So I should get that that's a 68, unless I'm totally nuts, but I think I'm right. So I get a negative of a 68 fifths, so I think I get negative 68 fifths. And we can check me on that, because it would be funny if that's the one that went horribly wrong. It's not a terrible skill, and I do want to just point this out, that it's actually a really good skill, in fact, that as you do these problems, you practice integrating on the calculator to check if you're right. The reason I say that is that integration on a calculator is going to be really important. You're not always going to be able to do it. You're not always going to be able to do it. Oh, I could have just math fracked my answer last time. Never mind. Anyway, so you won't always be able to integrate on a calculator on a test. It's not always a choice. And you won't always have to do it. But on the problems where you have to do it, if you've been checking this whole time and practicing, it's going to be a lot easier. So I'm going to go ahead and math frack it and see if we get the right answer. Hey, we did. That's exciting. All right, moving on. All right, so sometimes, and I think, yeah, we only have 2 problems left. So sometimes in multiple choice questions, you aren't asked to evaluate the integral. You're just asked to rewrite this as another integral. And then you really have to go the official way of switching the bounds. So in example 8, we are told to use u equals 2x plus 3. Which of the following is equivalent? Okay, so basically we have to do u sub, right? We have to do u sub, but we don't actually integrate. They just want us to substitute stuff. So if I follow their instructions and u is 2x plus 3, my du should be a 2 dx, meaning I get a du over 2 as my dx. So when I change the integral, I should get a root u and a du over 2. So immediately I cross off the ones that don't have the 1/2. See how this over 2? So immediately I say, oh, these two are wrong, right? Then I have to worry about the bounds. Well, the original bound was that x equals 3. Since u is 2x plus 3, my top u should be a 9. And that pretty much gets me to the point where I say, okay, cool, that's the right answer. I don't even have to bother to change the bottom bound because it's multiple choice. If you bothered to change the bottom bound, you would get that the bottom bound actually stays exactly the same. Oh, I'm sorry, no, the bottom bound goes from a -1 to being a 1, my bad. Sometimes I misread my own work. So if you wanted to bother with the bottom bound, when x is -1, you get that u is 2 times -1 plus 3, which is a 1, and sure enough, that's right here as well, right? But again, you only do as much math as you have to do before you realize you're right. Now, some of you are probably saying, but Hogan, once we got the 1/2, couldn't we have just recognized that the bounds definitely change, and since that makes D automatically wrong? And yeah, that's a solid good guess. All right, so go ahead and try this one. Here we're using u equals x squared minus 2. So my u is x squared minus 2, right? Which means my du is going to be at 2x dx, right? So du over 2x is my dx. When I replace this integral, I'm going to have this x cubed times my u to the 5th times a du over 2x. Well, an interesting thing happens. Two things, actually. One of these x's cancels. So I definitely have a 1/2, right? So I know there's a 1/2, but all the answers have a 1/2. So I have a 1/2, I have an x squared, I have a u to the 5th, and I have a du, right? So here's the problem. The problem is that I need to replace this x squared. Well, I know that I could solve this and say u plus 2 is my x squared. So now I could say that this is a 1/2 u plus 2 times this u to the 5th du, right? So I get that this is a 1/2 u to the 6th plus 2u to the 5th du. So all of that's fine, except I look and see that the 1/2 is distributed in this one. So I'm looking at a 1/2 u to the 6th plus 1/2 times 2 is just going to cancel, and I'm going to get a u to the 5th. So now I know this is what I'm looking for. Again, I've cheated and ignored the bounds, so I know that it's not the u to the 7ths, so it's not those. So I've narrowed it down to these two. Now, I could make the logical inference that the bounds are probably changing, and that makes C very unlikely to be a right answer, but let's just make sure. So I now need to worry about these bounds, right? So I have these question mark bounds that I don't know about. I'm not sure what they're supposed to be. I know that they're probably not the same numbers. It could mathematically happen, but it's unlikely. So I know that the top bound used to be x equals 3, and that u is x squared minus 2. So u should be 9 minus 2, or 7. Well, once I know that the top bound is 7, I'm pretty much done, right? Once I know that the top bound is 7, I can say, hey, that's my answer. It's B. Congratulations. All right, that is U-sub. I know it was a long video, but it's an important one.